Hey everyone, it's Dr. Walker. This is video 60C on rolling motion. Up to now, we've been talking about objects rotating about a fixed axis. How do we describe their motion if they're actually rolling? Let's consider the case of rolling without slipping. That means that the object is rolling on a surface and it's not sliding, it's not slipping. Let's look at the translational or the linear speed of the center of mass. Center of mass of this object here is at the center. So it's going to move linearly. To find the speed of the center of mass, we just take the derivative of the distance per time. The distance traveled as this object is rolling from this point to this point. That distance is s. And s is the same thing as the arc length, as you can see from this picture. We know that the arc length is defined as the radius times the angle. So we can plug in r theta into our ds here, and we're going to end up with r taken out of the derivative, r and then d theta over d time. So the derivative of theta with respect to time is the angular speed. So the velocity of the center of mass is r omega. Does that look familiar? It should. When we were talking about rotating objects, we said this thing is rotating with an angular speed omega, but at any point on the object has a linear speed v, which we said was r omega. Now we're saying that the velocity of the center of mass as it's rolling is the same r omega. We can come up with a similar equation for the acceleration of the center of mass if we take the derivative of the velocity with respect to time, and we plug in the rd omega for the d velocity, then we end up with r alpha for the acceleration of the center of mass. Now let's go ahead and take a look at the energy of a rolling object. A rolling object has both translational and rotational kinetic energy. So it has a sum of both types of energies. We can consider the translational motion of the center of mass and then the rotational motion of the object as a whole. In this picture, we can see that the two types of motions are separated. We consider the translational motion on the left here, and we can see that at a point at the bottom or middle or top, they're all moving with that linear speed, velocity of the center of mass. Then we can consider the rotational motion. A point at the bottom is moving with a speed v, but it's equal to r omega, and it's negative because it's going to the left. Then a spot in the middle is not moving at all, right, because it's rotating about this axis. And then a spot at the top has a speed v equals r omega. And for the rolling motion, we combine the translational and rotational motion. And we can see in this picture, it's pretty interesting, that if you sum up the two speeds, at the top you get 2v, in the middle here, you get the velocity of the center of mass. So you can see the center of mass is just moving in a straight line. And a point at the bottom is actually momentarily at rest because it's in contact with the ground here, and the object is rotating, but there's no slippage, right? This is rolling without slipping. So now that we know that a rolling object has both types of energies, we can write conservation of energy for the rolling objects. It looks just like the equation we had in the previous video. When we have an isolated system, the change in translational kinetic energy plus the change in rotational energy plus the change in gravitational potential energy is equal to 0. We can write all the terms individually if we want to. We just did it in the previous video, and we'll go ahead and do it again in an example that follows. Before we move on to the examples, let's do a conceptual question. A hoop and a disc of the same mass and radius are released simultaneously and roll down an incline. Which will reach the bottom first? So pause the video to think about it. We know that we can use conservation of energy as we have an isolated system. We know that we have potential energy to begin with, and we're starting from rest, so we don't have any kind of kinetic energy. I'm just assuming that released means released from rest here. So we only have potential energy, and then that's being converted. And when we get down to the bottom here, It's all kinetic energy, rotational kinetic energy and translational kinetic energy. There's no more potential energy when we have reached our lowest point. So let's go ahead and write out the terms. mgy initial equals 1/2 I omega final plus 1/2 mv squared. Now let's answer this question conceptually. Which one is going to have the higher speed? All of the potential energy is converted to kinetic energy. So it turns out, since they both have the same potential energy to begin with, because they all have the same mass, and they're started from the same height, then this sum has to be the same for both. So, whichever one has the lowest moment of inertia is going to end up having a higher velocity. So that's the trick to this kind of question. When you're racing objects that are rolling down an incline, an object with a smaller moment of inertia is always going to win the race. So which one has a smaller moment of inertia? Remember that the moment of inertia is bigger when your mass is concentrated far away from the axis of rotation. This moment of inertia is mr squared, while for the disk, it's 1/2 mr squared. So that means that the disk is going to win the race because it has the smaller moment of inertia out of the two.